Welcome to MarkScheme. Composite and inverse functions. Everything you need made visual. Every morning, you run a two-step routine. Socks first, then shoes. That's a chain of two operations, one feeding into the next, a composite. Now suppose you want to undo it, to get back to bare feet. You do not take your socks off first. You can't. You reverse the whole thing. Shoes off, then socks off. To undo a chain, you flip the order and undo each step. That single idea, chaining operations and reversing them, is the entire topic. Composite functions build the chain. Inverse functions reverse it. Let's make it exact. Here's exactly what this covers. Straight from your syllabus. IB analysis and approaches, standard level, 2.5. Composite functions, f of g of x, and why the order matters. The identity function. The inverse function, f inverse, as the undo of f. The inverse seen as a reflection in the line y equals x. And how to find the inverse? By algebra. Watching domain and range swap over. This builds on functions and domain and range from 2.2 and the line y equals x from the graphs video. If those are shaky, watch them first. Start with the composite. Think of each function as a machine. You feed in x, it spits out a number. A composite just wires two machines in series. The output of the first becomes the input of the second. Feed x into g, and out comes g of x. Now push that straight into f, and the final output is f of g of x. We write it with a little ring. F composed with g of x equals f of g of x. But here's the trap that catches everyone. Read the notation from the inside out. The is tucked inside next to the x. So g runs first, and f runs on its result. Right to left. The machine nearest the x goes first. Before inverses, meet the quietest function of all, the identity. It does absolutely nothing. Whatever number goes in, the exact same number comes out. I of x equals x. Its graph is the perfectly straight diagonal, y equals x. And that line is about to become the star of the show. Compose anything with the identity, and you get that thing back, unchanged. Why do we care? Because it gives us the precise definition of an inverse. The inverse of f is the function that undoes it so completely. That f followed by f inverse leaves you exactly where you started. It equals the identity. That's the target. Here's the beating heart of the whole idea in one animation. The inverse of f, written f with a little -1, is the undo button. Take the function f of x equals 3x. It triples. Watch a single number make the round trip. Send 4 into f. It triples to 12. Now send that 12 straight into f inverse. It divides by 3, and out comes 4 again. Exactly the number we started with. The undo canceled the do. That is what an inverse is. F inverse of f of x brings you home, back to x, every single time. That undo has a stunning picture behind it. If f sends a to b, the point A, b sits on its graph. Then f inverse must send b back to A. So the point B, A sits on the inverse. The coordinates simply swap places. And swapping the two coordinates of every point is exactly what reflecting in the line y equals x does. So watch the graph of f literally fold across that dashed diagonal. Every point carries over to its mirror image. And what lands on the other side is the graph of f inverse. The blue curve, becoming the gold one. The inverse isn't a new mystery. It is your original function, reflected in y equals x. If you can draw f, you can draw its inverse just by flipping it over the diagonal. Take one point to be sure. On f, the point 2.2, 3.6. Reflect it, swap the numbers, and you get 3.6, 2.2 on the inverse. Same two numbers, coordinate straighted, mirror image across the diagonal. Beautiful. And it's your fastest way to sketch any inverse. That reflection hands us a foolproof recipe for finding an inverse by algebra, the swap and solve method, and its 4 short steps. 1. Write y equals f of x. 2. Swap x and y everywhere. 3. Solve the new equation for y. 4. That expression is your inverse, f inverse of x. And step 2 isn't a magic trick. It's the reflection in disguise. Flipping over equals x swaps the two coordinates of every single point. So swapping the letters x and y in the equation does precisely the same job. Understand that, and you'll never forget the method. Let's build a ladder of examples, easy to hard, all my own numbers, IB style. Example 1. Take f of x equals 2x plus 1 and g of x equals x squared. Let's compute both composites and see, concretely, that the order changes the answer. First f composed with g. The inner function is g, so g runs first. G of x is x squared. Feed that into f, which doubles and adds 1. 2 times x squared plus 1. So f of g of x is 2x squared plus 1. Now reverse it. G composed with f. This time, f runs first, giving 2x plus 1, and g squares whatever it's handed. So we square the bracket. 2x plus 1, all squared, which expands to 4 squared plus 4 plus 1. Look at the two results side by side. They are completely different functions. Composition is not commutative. F of g is not g of f. Put a number in to feel it. At x equals 3, f of g gives 2 times 9 plus 1, 19. But g of f gives 7 squared, 49. Same functions, same input, wildly different outputs, purely because of the order. Always respect which one is inside. Example 2. A clean linear function, f of x equals 3, x minus 2. Find its inverse, then prove we got it right. Straight down the 4 steps. Right, I equals 3x minus 2. Now the key move. Swap x and y. X equals 3y minus 2. From here, just solve for y. Add 2 to both sides. X plus 2 equals 3y. Divide by 3. Y equals x plus 2, all over 3. That is the inverse. F inverse of x equals x plus 2 over 3. Never trust an inverse without checking it. And the check is a composition. Feed the inverse into f. 3 times x plus 2 over 3 minus 2. The 3 cancels the divide by 3, leaving x plus 2 minus 2, which is just x. We landed back on the identity, so the inverse is correct. That one line of working is worth a mark, and it catches slips. Example 3 steps up, and it exposes something students forget half the time. Take f of x equals the square root of x minus 1, defined for x at least 1, so its outputs are 0 or above. Find the inverse, and track the domain and range. Same recipe. Y equals root x minus 1. Swap. X equals root y minus 1. To free the y, square both sides. X squared equals y minus 1. Then add 1. Y equals x squared plus 1. So the inverse is x squared plus 1. But we are not finished. And this is the mark most people drop. A plain x squared plus 1 would be a full parabola, which is not 1-to-1 and could never be an inverse. The domain saves us. The original f took inputs of at least 1 and produced outputs of 0 or more. Under an inverse, those swap. The inverse takes inputs of 0 or more and returns values of at least 1. So we must write x squared plus 1 for x greater than or equal to 0. The domain of f becomes the range of the inverse, and the range of f becomes its domain. Always state it. Example 4. The genuine step-up. It fuses both halves of the topic. With f of x equals 2x minus 1 and g of x equals x plus 4, find the inverse of the whole composite. A composed with g. 2 moves. Build the composite, then invert it. Build first. G is inner, so g runs first. X plus 4. Feed it to f, which doubles and subtracts 1. 2 times x plus 4 minus 1, which tidies to 2, x plus 7. Call that single function h. Now invert h with swap and solve. Y equals 2x plus 7. Swap to x equals 2y plus 7. And solving gives y equals x minus 7 over 2. There's the inverse of the composite. Here's the deep payoff. And it's our socks and shoes from the very start. There's a shortcut law. The inverse of a composite reverses the order and inverts each piece. G inverse composed with F inverse. Undo the last thing first. Check it. G inverse is minus 4. F inverse is x plus 1 over 2. Compose them in that reversed order, and you get x minus 7 over 2. The identical answer. Shoes off, then socks off. 2 edge cases that quietly wreck answers. First, a notation trap. F inverse is not 1 over f. That little minus 1 is not a power. It does not mean reciprocal. For f of x equals 3x, the inverse is x over 3. The undo. 1 over f would be 1 over 3x. A totally different thing. Inverse undoes. Reciprocal divides. Keep them apart. Second, and deeper. Not every function even has an inverse. To be reversible, a function must be 1-to-1. Each output must come from exactly one input. The horizontal line test from the function's video. A full parabola fails it. The height 4 comes from both plus 2 and minus 2, so the undo wouldn't know which to return. The fix is to restrict the domain. Keep only x greater than or equal to 0. The right half in green, and now it is 1-to-1, with a clean inverse. Root x. Examiners love handing you a restricted domain for exactly this reason. Now the exam craft other channels skip. 4 rules to bank. 1. For any inverse, reach for swap and solve. Write y equals f of x, swap x and y. Solve for y. It never fails, and it works when guessing won't. 2. Always check by composition. Feed your inverse back into f, and you must get x. That single line earns a mark and catches errors. 3. If a function isn't 1-to-1, restrict its domain first. X at least 0 for a quadratic, and state that restriction. And 4. Read a composite right to left. The inner function runs first. And remember that the domain of f becomes the range of f inverse. They trade places. Master those, and inverses become free marks. Finally, the 3 traps that cost marks. 1. treating f of g as the same as g of f. They almost never are. Order matters. And the inner function always runs first. So read right to left. 2. Writing f inverse as 1 over f. The little -1 means undo, not reciprocal. A completely different function. And 3. The sneakiest. Forgetting that domain and range swap under an inverse, and so leaving the inverse's domain unstated. After square root especially, you must pin down which half you keep, or your inverse isn't even a function. Dodge these 3, and composite and inverse questions are some of the most reliable marks on the paper. And that is SL 2.5, fully covered. Composite functions, and why the order matters, the identity function that does nothing, the inverse as an undo, its reflection in the line y equals x, how to find it by swapping x and y, and the way domain and range trade places. Next in the course, we turn to the single most examined curve in the whole syllabus, the quadratic function. For more, that's markscheme.app. See you there.